Conditional probability tells us how likely event A is when we already know that event B has happened. Think of it like checking the chance that it will rain, A, given that the sky is already cloudy, B. The mathematical rule is P of a given B equals P of a intersect B divided by P of B. Here P of a intersect B is the probability that both A and B occur together, and P of B is the probability that B occurs at all. The formula works only when P of B is not 0, because dividing by 0 is impossible. Example, in a deck of 52 cards, let A be the card is a king and B be the card is a face card. P of A intersect B equals 4 over 52, 4 kings. P of B equals 12 over 52, 12 face cards. So P of a given B equals 4 over 52 divided by 12 over 52 equals 4/12, which is 1/3. This means that once we know the card is a face card, the chance it is a king is 1/3. The multiplication rule lets us find the probability that several events happen one after another. For two events, it says P of A intersect B equals P of A times P of B given A. The first factor is the chance that A happens, and the second factor is the chance that B happens given that A has already occurred. For three events A, B, C, we extend it. P of A intersect B intersect C equals P of A times P of B given A times P of C given A intersect B. In general, for n events E1, E2, En, P of E1 intersect En equals P of E1 times P of E2 given E1 times P of E3 given E1 intersect E2 times P of En given E1 intersect En minus 1. Real-world picture. Imagine picking balls from an urn without putting them back. The chance of drawing a red ball first is P of R1. If the first ball was red, the chance the second is also red changes, so we use P of R2 given R1. Multiplying all the conditional chances gives the overall chance of a whole sequence. Explanation: Bayes' prime theorem reverses the conditioning direction. It is useful when we know the likelihood of evidence given a cause, and we want the probability of the cause given the evidence. The theorem states, P of a given B equals P of B given A times P of A divided by P of B. Here P of A is the prior probability of A, P of B given A is the likelihood, and P of B is the overall probability of B, often found by the law of total probability. Example medical test. Let A equals patient has disease, B equals test is positive. Suppose prevalence P of A equals 0.01, the test correctly detects disease with 0.99, P of B given A and gives a false positive 0.05, P of B given a complement. Then P of B equals 0.99 times 0.0, 1 plus 0.05 times 0.99 equals 0.0594. Bayes gives P of a given B equals 0.99 times 0.01 divided by 0.0594 approximately 0.166, meaning a positive test still only gives a 16.6% chance of disease. In reliability engineering, a could-be system fails, B equals alarm sounds. Bayes helps decide whether to shut down the system based on the alarm. Two events are independent when the occurrence of one does not change the chance of the other. The formal test is P of A intersect B equals P of A times P of B. If this equality holds, knowing that B happened gives no extra information about A and vice versa. Example: toss a fair coin twice. Let A equals first toss is heads, B equals second toss is heads. P of A equals 0.5, P of B equals 0.5, and P of A intersect B equals 0.25, which equals 0.5 times 0.5, so the tosses are independent. In engineering, the failure of one component may be independent of another if they operate on separate principles. Explanation: a practical way to check independence is to compare conditional and unconditional probabilities. If P of a given B equals P of A and equivalently P of B given A equals P of B, the events are independent. This follows because P of a given B equals P of A intersect B divided by P of B, which equals P of A times P of B divided by P of B, which simplifies to P of A. Counterexample: draw a card from a deck without replacement. Let A be first card is an ace, and B be second card is an ace. P of A equals 4 over 52, which simplifies to 1 over 13. After an ace is drawn, only 3 aces remain, so P of B given A equals 3 over 51, approximately 0.0588, which is not equal to 1 over 13, approximately 0.0769. Hence, the two events are not independent. Remember to verify that both conditional equations hold. Sometimes one direction may look equal by coincidence, but the other does not. Independence and mutual exclusivity are opposite ideas. Mutually exclusive events cannot happen together, so P of A intersect B equals 0. If they were also independent, the product P of A times P of B would have to be 0, meaning at least one of the events must have probability 0, a trivial case. Common exam trap. Students think if events cannot occur together, they are independent. Example, rolling a single die, let A equal outcome is 1, B equal outcome is 2. They are mutually exclusive, both cannot occur, but they are not independent because knowing that A occurred tells you B cannot occur, changing its probability from 1/6 to 0. The correct test for independence is the product rule, not the exclusivity rule. Cards without replacement. Find the probability of drawing 2 red cards in a row from a standard deck. P of first red equals 26 over 52 equals 1/2. After one red is removed, P of second red given first red equals 25 over 51. Multiply 1/2 times 25 over 51 gives approximately 0.245. To machine selection. A factory has machine 1 with reliability 0.9 and machine 2 with reliability 0.8. One machine is chosen at random. What is the probability the selected machine works? P of work equals 0.5 times 0.9 plus 0.5 times 0.8 equals 0.85. If the chosen machine fails, use Bayes to find which machine it likely was. Urn problem. An urn contains 3 white and 2 black balls. 2 balls are drawn without replacement. Find P of first white and second black. P of first white equals 3 over 5. P of second black given first white equals 2 over 4 equals 1/2. Product equals 3 over 5 times 1/2 equals 3 over 10. Explanation. Exam style questions often follow patterns. Computing P of a given B from a table. You are given a joint probability table for events A yes or no and B positive or negative. Sum the cell for intersect B and divide by the marginal total for B to get P of A given B. Determining independence. You receive marginal probabilities P of A, P of B, and a joint probability P of A intersect B. Check if P of A intersect B equals P of A times P of B. If they match, the events are independent. If not, they are dependent. Bayes in reliability. A system consists of 2 blocks in series. Each block fails with probability 0.02. An alarm goes off if any block fails. Given that the alarm sounded, find the probability that both blocks actually failed. First, compute P of alarm equals 1 minus 0.98 times 0.98, which is 0.0396. The joint failure probability is 0.02 times 0.02 equals 0.0004. Apply Bayes. P of both fail given alarm equals 0.0004 divided by 0.0396, approximately 0.0101, about 1%. These templates help you structure your solution quickly during exams.